2.1, using inductive reasoning. We're going to describe patterns and use inductive reasoning. So geometry, like much of science and math, was developed partly as a result of people recognizing and describing patterns. So we are going to discover patterns and use them to make predictions. So looking at a visual pattern, describe how to sketch the fourth figure in the pattern. Then sketch the fourth figure. So you take notice, each circle is dividing by twice as many as the one prior. So there's only 2 halves here, then there's 4, then there's 6, so the next one should have 8. So figure 4, we're going to draw a circle and have 8 equal parts. And you take notice that it's shading as it comes to figure 2. It's the left shade just up from center. So let me just do this real quick. I just want to make this a little bit thicker. Each circle is divided to 2 more than the prior. Not twice, but just 2 more than the prior. Right? So it's counting by 2s. Now looking at a number pattern, so you're trying to see what kind of thing is going on from the first number to the second number, from the second number to the third number, and etc. So from the first number to the second number, I can see that's times 3, and this is times 3, and so is this times 3. So the next 3 numbers in the pattern is going to continue times 3. So 189 times 3 is negative 567. Times 3 is negative 1701. And then times 3 again is negative 5103. So there's the next 3 numbers in that pattern. Oops. Okay, so you should try sketching the 5th figure in the pattern in example 1, and then go to the next page and try to describe the pattern in the numbers. So hopefully in the first one you did draw a circle and try to create 10 parts, and you shaded that one on the left just from center. And in the second one, hopefully you took notice that it was adding by 0.02. So you add 0.02 to 5.07, then to 5.09, then to 5.11. A conjecture. A conjecture is an unproven statement that we just make based on observations. We use reasoning when we find a pattern in specific cases, and then we write a conjecture for the general case. So we're going to write a conjecture. If we're given 5 collinear points, make a conjecture about the number of ways to connect different pairs of the points. Okay, so the first thing I need to do is make a table. So I have 1 point, and then 2 points, 3 points, 4 points, and then 5. So then we're going to think about the number of connections. So connections, all right, I can't connect anything in the first one. Right? In the second one, I can only connect it between the two of them. So there's only one way. In the third one, I can connect the first to the second, the first to the third, and the second to the third. So there are 3 ways. In this one, I can connect the first to the second, the first to the third, the first to the fourth. I can connect the second to the third, the second to the fourth, and I can connect the third to the fourth. So that is 6. So let's see, can we find a pattern? Between the first two, I see it's going up by 1, then it's going up by 2, then going up by 3. So I expect this to go up by 4, and my answer would be 10. So my conjecture would be that you can connect 5 collinear points ten ways. Okay? Let's make and test a conjecture. So numbers such as 3, 4, and 5 are called consecutive integers, okay, when it goes one right after the other in order. Make and test a conjecture about the sum of any 3 integers. Find a pattern using a few groups of small numbers. So it actually doesn't say about the sum of any it says any 3 integers. I think it's supposed to say any 3 consecutive integers. Consecutive integers, since they were talking about that prior to. So consecutive integers, so think about integers 3, 4, and 5. What happens there? The sum of that is 12. Think about -1, 0, 1, 0. -3, 2, oops, and 1. It's -6. So to make a conjecture, you need to look and see if you can notice some kind of pattern that's going on. So if I look at my end result and try to compare it with the numbers in my consecutive numbers, if I look at the middle number, that one's a little hard there in the middle with the 0. If I take notice between the 4 and the 12 and the -2 and the -6, I can actually see that the sum of any 3 consecutive integers is actually 3 times the middle integer. So test it with another set of 3 consecutive integers. Maybe go larger integers this time, 10, 11, and 12. 10, 11, and 12, I add those together, I get 33. Is 33 3 times the center? Yes, it is. So you have 2 to try. So go ahead and see if you can do those. Remember, the 7 collinear points is going to be continuing what we were doing in that prior example. And we had our numbers were number ways from 1 was 0, 2 collinears was 1, 3 was 3, 4 was 6. We made a conjecture about 5, and we noticed that it was counting up by basically the counting numbers. So our conjecture would be that there are 21 ways to connect 7 points. Collinear points, right? For the second one, any 3 negative integers, what is the sign of their product? So you have to you just multiply 3 integers together, negative integers. And conjecture is that the sign of the product of 3 integers, 3 negative integers, is negative. Okay, so in order for a conjecture to be true, it has to be true for every case. We can show that conjectures are false by just coming up with one example, which is called a counterexample, that proves it. So we're going to look at, the student makes the following conjecture about the sum of 2 numbers. Find a counterexample to disprove the student's conjecture. So we have 2 numbers. The sum is always greater than the larger number. So an example of 2 numbers, adding them together. What if I added 2 negative numbers together? If I add 2 negative numbers together, is negative 7 greater than the larger number? The larger number is the one that's least negative. No, that's not true. So it could be any example of that sort. Maybe adding a number to 0. This is saying then my sum, 3, has to be greater than the larger number that I'm adding, 3. And that also isn't true. For the counterexample, you only have to come up with one. And I just have a test practice here. We're going to look at which conjecture could a high school athletic director make based on the graph to the right. Okay, so what do we have a graph of? We have a graph of girls registration over year. So it's participation. is there anything mentioned about boys? So we look at answer A. Answer A, it's girls, not boys at all, right? Boys aren't even mentioned. So it can't be that one. What about more girls are playing soccer today than in 2001? And you can see that this book is a few years old. So I do agree with that right now. So we'll mark that one for now. But we need to check the other answers. C, more people are playing soccer today than in the past because of 2000. Does it give reasonings? No reasonings. It's not in the graph. And what about D? The number of girls playing soccer was more in 2001 than in 2007, and that's just not true. So my original answer, thinking B, is correct. All right, you have some to try. Remember, a counterexample is just showing one example that proves it false. Okay, to prove the conjecture that the value of x squared is always greater than the value of x, think that x could equal 0, x could equal a fraction. It's not saying that it has to be a particular type of number. And looking at the graph in example 6 to make a conjecture that could be true, so we could say that the number of girls playing soccer will increase. And the proof of that is that if you look at the graph, it has increased over the last 10 years. So to close the lesson, how do you use inductive reasoning in mathematics? You use it to make patterns, or find patterns, I should say. To find patterns and make conjectures.